Hello there, ATSEVS533 students. Dr. John Schrage here after a set of strange little technical setbacks. Anyway, I apologize for those of you who had problems getting to this video and so on. I think we have everything under control. Just had some technical problems and so on. Today we're going to continue our stuff in Module 3. We're going to be extending our ideas about future climate change that we can learn about from science, from physical climatology, especially from numerical models, into the more distant future. Hold on just a second here, there we go. Last time we were looking at a range of possible outcomes with regard to moisture and temperature and so on that we could see, say, out to the middle of the 21st century or something like that. And that's very important for like policy and societal impacts and so on, and all kinds of things that frankly are well treated in other courses that you take. Today I want to start thinking about a little bit farther into the future. That it starts becoming difficult to exactly figure out, how to make policy plans for, possible collapse of the West Antarctic ice sheet or something like that, when those kind of things could very well be literally hundreds of years into the future. We don't really make policy decisions on that kind of time frame. And what we're going to find out is there's all these really scary things that could go wrong in the climate system. And so, to maybe start off on something a little less tragic, let's think about something a little bit more optimistic. Like, for example, let's just pose a question here. What would actually happen to the future climate if we could somehow just stop emissions today? Okay, for whatever reason, humans just disappeared. Okay? We're not talking like we stopped emissions because there was a thermonuclear war and now there are no humans. I mean, then the climate's a whole different story. I mean, I don't know. We got biblically raptured off the planet or something like that. I don't know. Somehow or other, all our emissions, not just carbon dioxide and things like that, but also like all the particulate matter and so on that is of anthropogenic origin and so on. So this is a completely unrealistic scenario, but it tells us something about what's going on now and what would happen in the future based on the things that we're doing now. Well, first we'd have to know what's going to actually happen. We're not adding any more in this hypothetical scenario. We're not adding stuff to the atmosphere anymore, but we are still dealing with the stuff that is already there. Now, the issue here is that the stuff that we add to the atmosphere has a residence time, that is an expected amount of time that any given carbon dioxide molecule, methane molecule, halocarbon molecule, aerosol, black carbon aerosol, whatever, there's an expected amount of time for those such things to remain in the Earth's atmosphere, and how long the various greenhouse gases and aerosols persist in the atmosphere varies. It varies on a very wide range of different timescales, ranging from days to thousands of years. For example, most aerosols in the Earth's atmosphere, those little solids suspended in the atmosphere, mineral dust, black carbon, stuff like that, most of those aerosols have a lifetime on them no more than weeks, maybe even days. They're fairly easily washed out of the atmosphere by precipitation, or just gravity gradually pulls them back to the ground. That's called sedimentation. On the other hand, there's methane in the atmosphere. Methane does not, in general, get washed out of the atmosphere by precipitation. It generally doesn't. It generally doesn't precipitate or anything like that. It's a gas. So, but it does, on the other hand, have a fairly short lifetime of only about 10 years before it is oxidized into water molecules in the presence of an atmosphere with oxygen in it. Nitrous oxide is another important greenhouse gas that we talked about way back in the first module of the course. Has a mean life residence time of about 100 years, and certain halocarbons, in this case hexafluoroethane, which I don't know anything about, other than it's one of the halocarbons that we use in manufacturing and so on, has a residence time on the order of tens of thousands of years. Because it's not water soluble, it's virtually impossible to get the stuff out of the atmosphere once it's there. Well, look how many orders of magnitude different these residence times are. And so, hold on just a second here, there we go. So, notice, by the way, I haven't even mentioned carbon dioxide yet. The whole business of carbon dioxide gets a whole lot more complicated because there's all these different processes. There are multiple processes that add carbon dioxide to the atmosphere, and there are multiple processes that remove carbon dioxide from the atmosphere and store it in the different reservoirs of the carbon cycle, like the land biosphere and the mixed layer of the ocean and so on. And so there's all these biogeochemical processes at work and so on, and they all operate on different timescales, and that's why studying the carbon cycle is a thing, especially in like an Earth System Science course. Hint, hint, we need an Earth System Science course. So, we gotta figure out what's going on. I mean, if carbon dioxide is our main pollutant that we're worried about in terms of its radiative forcing driving future climates, we need to understand how it gets out of the atmosphere once we are gone in this we're not emitting anything scenario here. And the answer is, a lot of it gets removed right away. Within the course of a few years, maybe no more than a few decades, an awful lot of the carbon is actually removed and stored in bad forms, like as carbonic acid in the ocean and things like that. But a fair amount of the total amount of carbon dioxide in the Earth's atmosphere does get removed fairly quickly on climate timescales. But it does take on the order of thousands of years to start returning to pre-industrial levels. We've seen that before. And as a result of these complicated businesses of all these different constituents of the anthropogenic mess that we've added to the atmosphere, we have to keep track of all the different residence times here. The aerosols that were out of the atmosphere, they'll be gone in no time. A few weeks. Well, that's complicated because the aerosols they have radiative forcings associated with global dimming and so on. The methane that we're adding to the Earth's atmosphere could be gone in no more than a few decades. You might be surprised to know that, in fact, if we stopped emitting methane in the atmosphere, certainly no more than like 50 years, all the anthropogenic methane would be gone. The the N2O concentrations would return to pre-industrial levels in no more than a few centuries, but on no meaningful time scale that we can think about in terms of environmental issues and so on would carbon dioxide ever come back to its pre-industrial levels. It just is, the carbon cycle is too slow. We're talking on the order of thousands and thousands of years. So there's going to be some anthropogenic stuff out fairly fast in the atmosphere in this scenario in which we're getting rid of everything, getting rid of all human emissions. But the carbon dioxide is going to be there for a long time to come, millennia. Even if we stopped emitting. That means that the climate change would continue. It has a lot of inertia, to use the right word there. The climate doesn't change quickly or immediately based on the forcings that are already there. So, like for example, these are some simulations from the IPCC report that show what would happen under different emission scenarios. We have this is global mean temperature with respect to, I think 2005 is the zero line, and then we see what happens from there. And, like the red set of curves right there, that's an ensemble of runs with constant emissions in the future. That's a type of scenario that we could emit. We could talk about, like, if we just didn't increase our amounts of emissions. But look what's going on with those blue curves there, where we have zero emissions. Let me zoom this in a little bit right here. Sorry about that here for a second. Let me zoom in on that. See how in the zero emissions scenario, you would think the temperatures would go up more slowly than they did in the scenarios where we were emitting, but actually the opposite turns out to be true. You have a few years there where the temperature actually spikes upward. What the heck's going on here? If we're gone, if we're not emitting anything or whatever, why is global temperature actually spiking quite a lot there in the near future? Well, it has to do with the fact that all these different anthropogenic things that we've been adding to the atmosphere, some had positive radiative forcings and some had negative radiative forcings. And in fact, the one with that had overall a negative radiative forcing and was helping keep the Earth cool through global dimming was aerosols. And the aerosols will be gone in no more than a few weeks. All that black carbon, all that sulfate and so on, certainly not more than like a year or so, all that stuff that has a negative radiative forcing will be gone. The planet's temperature is going to spike. Oh. But it is true that with time there's inertia in the climate system and so on, and we'll start, the global temperature will start, it'll decrease back to where it would have been with constant emissions and so on. So even we suddenly live in a happy world with no emissions whatsoever and our whole economy is driven by renewable sources, even that doesn't solve our problem, and in fact in the short term makes our problems worse. As a consequence of this large inertia is the right word we use in the climate and carbon cycle, long-term temperature turns out to be largely determined not by these little changes, for a few years of the temperature spiking due to the aerosols changing and so on, but by the total amount of emissions that we've had in the past. Even if we at some day in the future just stop emitting tomorrow, So tomorrow, somehow or other, we all discover some green renewable source of energy. The problem is, the climate that we're going to get is going to be dependent on all those emissions we've had since the Industrial Revolution. They're totally carbon dioxide emissions that have accumulated over time. And from the climate's point of view, it doesn't matter when those greenhouse gases were added. Whether they are something we've cut back now or whether it's something we cut back 10 years ago or whatever, it's just the total amount of carbon dioxide we've added since the Industrial Revolution. And this ends up telling us something very important about what we have to think about doing and plan about doing for the future. If we're going to have some kind of limit to how much global warming we're going to have, for example, it's often talked about this 2 degrees Celsius threshold, that we want to keep climate change to less than 2 degrees Celsius from pre-industrial. The problem is we effectively have a budget of carbon dioxide to work with. Effectively, we have a certain amount, look, to get to a certain climate change in the future, if that's all we're going to be able to allow, then guess what? There's a certain number of gigatons of carbon we can add to the atmosphere between the Industrial Revolution and someday, and that's it. We got to parcel it out between now and then. Otherwise, we have to make even stronger cuts of the emissions later. Now, if we set a higher climate target, like we're willing to tolerate more than 2 degrees Celsius, then we have a higher total amount of carbon dioxide we can emit between the Industrial Revolution and the day we stop burning fossil fuels. Which gives us a chance to delay our necessary reductions in carbon emissions. But that's kind of a losing game too. Now notice how we've kind of been playing a slippery little game here. We've been talking about this idea of like a threshold, that we were like willing to tolerate. What's the right word here? We're gonna have a target of like 2 degrees Celsius or whatever here. And earlier edition of the IPCC report had a nice table that talked about these kind of things. This is an example of having a type of target that's based on global mean temperature, where we can say, you know, we are going to have a target. We're not going to let the temperature get more than a certain amount above, say, pre-industrial. And that's going to turn out to be very useful in a physical climatology class. In contrast, for example, we could have a type of target where we were limiting mitigation costs, for example, where we could say we want to prevent climate change in such a way that we are spending no more than a certain amount of money on reducing our carbon emissions and so on. And after that, we can't have any more costs. We're limiting it by the costs. We'll talk more about that in just a little bit, and also in the 4th module of the course. We could have a very tricky, although this is what the public wants, where we could talk about it in terms of like we're limiting the impacts of the global change, where we're willing to say we are going to not let the climate change get so bad that we cause these changes to ice sheets, or these changes to the distribution of hurricanes or whatever. But that's awfully hard to actually figure out like what that means in terms of emissions and so on. We're going to stick with this, generally, this idea of limiting ourselves to a particular temperature change, because that seems like the most scientific of those ideas, even though there's important policy applications for the other ones. Now, before we go on to the second part of this lecture and start talking about these long-term climate changes and what they mean, let's answer a couple quick questions first. Question 1. Which of the following anthropogenic pollutants has the shortest residence time in the atmosphere? Is it aerosols, carbon dioxide, methane, or nitrogen? Oh, that shouldn't be too hard. Make a choice from those 4 options and get a little feedback before you go on to question 2.